Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 24 from the course, but make sure you have watched the previous ones before viewing this one. In this lecture, we would be discussing a very important topic, that is the shapes of the orbitals, that is the S, P and D. Well, we will not be discussing the shapes of the f-orbitals because they are not a part of our curriculum. So let us begin the lecture. To begin with, we will quickly revise what is an orbital. Well, Bohr's orbits, they were fixed. With the coming of Heisenberg's uncertainty principle, we came to know that we cannot fix the position of an electron at a particular time. So came with that the concept of an orbital, which is a region in three-dimensional space around the nucleus where the probability of finding the electron is maximum. But can we draw a real picture of an orbital? Well, we cannot do that, and we cannot in fact draw sharp boundaries of the region of an orbital also. But still, if we want to have an electron cloud representation of an electron, what do? Well, we will simply indicate the electron density in the space around the nucleus by dots. Right? So this is a diagram showing you the difference between an orbit and an orbital, which we've discussed in the previous lectures. Just quickly revising, orbit, this is a two-dimensional picture. It is a planar orbit, and then we have an orbital which is a 3D representation of the electron cloud, right? So the dots, they signify that wherever there are more dots, that is, there is more density of these dots, there is more probability of finding the electron in that region. And then where there are less dots in a region, this shows that there is less probability of finding an electron in that region. Now, if we draw a line around this region in such a way that we cover about 90 to 95% of these dots, well, we will get the shape of an orbital. Then that diagram, which is giving us the shape of an orbital, this is called as the boundary surface diagram for an orbital. And all the orbitals, the S, P, D, F, depending upon the probability density, they are going to have different shapes, and that is what we are going to discuss in this lecture. So from the knowledge of the quantum numbers, we know that S subshell has one orbital, P subshell has 3 orbitals, D subshell has 5 orbitals, F subshell has 7 orbitals. And all of these orbitals, they are going to have different shapes depending upon the probability density and the directional nature of the various orbitals. And probability density is one thing that we studied while we were discussing the Schrodinger wave equation. And there we studied about the two wave functions. First was the wave amplitude, that is psi, which has no physical meaning of its own, but it is simply a mathematical function of the coordinates of the electron. And next we have the probability density, that is psi square, which has a physical meaning, and this is going to give us the probability density of electron in a region of space. And if we plot a graph of these two wave functions, psi and psi square, as a function of radius, together they are going to provide us the knowledge about the various shapes of these orbitals S, P, D, F. So let us learn about these graphs between the two wave functions as a function of radius. So first let us see the shape of the s orbital. For s orbital, L is 0. So that means in the s subshell, we have only one s orbital, right? M is going to be 0. That is one value for M. When we plot a graph of the wave function psi as a function of r, that is the distance of the electron from the nucleus, for the 1s orbital and the 2s orbital, that is 1s is n equal to 1, l is 0, and 2s is n equal to 2, l is equal to 0, we will see that the plots are going to be different. So these are the graphs of these plots you can see, and now let us discuss them. We have psi on the y-axis, we have the radius of, that is the distance of the electron from the nucleus on the x-axis, right? So we have psi as a function of r. What do we see? When the distance that is very near to the nucleus, we find the probability of the electron to be maximum. So psi is maximum over here. So this means the probability of finding the electron is maximum near the nucleus. And as the distance increases, the psi, the probability is decreasing very sharply, and then this is becoming stable and almost equal to 0. Right? So this means that as the distance is increasing, the probability of finding the electron, that is decreasing. Then we have a graph for the 2s orbital, again for psi and r. What is the difference over here that you see is that yes, near the nucleus, the probability is maximum. As we are moving away from the nucleus, the probability is sharply decreasing. Then this becomes 0 over here, right? So this is 0. So the probability of finding the electron has become 0. And in fact, it has gone down negative. And then after some time in the negative, the probability starts increasing, becomes positive, and then it becomes stable, almost 0, as the distance is increasing from the nucleus, right? So what do you find over here is that there is one point where the probability of finding the electron is 0. And that point, where the probability of finding the electron is 0, that is called as the nodal surface or node. In fact, in the graph you can see that the probability of finding the electron is even negative. Well, this is the drawback of this graph because the probability cannot be negative. So there was a thought that there should be some better representation of the probability density for an electron, and hence a German physicist, Max Born, he plotted a graph between psi square and r. And you will see that the graph again for 1s is exactly similar to this graph. There is no change. But when you see the graph for 2s, what do you find? Well, the probability again does come to 0 at a particular distance from the nucleus. And from 0 again it has started increasing. Then there is some maximum point of probability, and then again that probability is becoming 0 and almost near 0. Then this becomes again stable and less probability as the distance is increasing, right? So again we have a probability of finding the electron 0. So we have one node again for the 2s orbital, but now it is not going into the negative. So we can take this as a better representation of the probability density for an electron. Right? And you will find when the plots are drawn for 3s, 4s also, that the number of nodes, that is the region where the probability of finding the electron is 0, this increases with the increase of principal quantum number n. And in other words, this means that the number of nodes for 2s orbital we have seen is 1, for 3s it is going to be 2, and so on, and for 1s it was 0. Right? So this is what you see from the graph, and this is very important for you to remember that the number of nodes, they are increasing with the increase in principal quantum number. So let us see now further some important points about the shape of these orbitals. So here is a diagram which is showing the probability density plot for 1s and 2s orbitals also. According to the dot representation also, you can see what is the region where the electron density is going to be maximum, and this is the boundary surface diagram that is drawn. From these, what we have come to know is that 1s, 2s orbitals, they are spherically symmetrical. That is the probability of finding the electron at a given distance. This is equal in all directions, and hence the s orbitals, they are non-directional. Okay, so this is one important thing that you have to remember, that these are non-directional. The size of the s orbitals, they increase with the increase in n. You can see that the 1s orbitals, they are smaller in size than the 2s orbitals. That means the size for 4s is going to be more than 3s, going to be more than 2s, and least is going to be 1s. And then what about the nodes? We have a general formula for the nodes. The ns orbitals, they are going to have n minus 1 nodes. This means that the 2s orbital, this has one nodal plane, whereas the 1s has no nodal plane, right? And the electron, this is located further away from the nucleus as the principal quantum number increases. I hope this all is clear to you, that we have the s orbitals which are spherical in shape, they are non-directional, the size is increasing with the increase in n, and the number of nodes for the s orbitals is going to be n minus 1. This is one of the questions which is frequently asked in the examination about the number of nodes in the various orbitals. So next we have the p orbitals, and if you see the diagram for the p orbitals, this is also based on the various graphs that were drawn between psi and r, psi square and r. So we have this boundary surface diagrams according to those plots. So you will see that we have p orbital, L is 1, so L is 1, so the possible values of M, they are 3, that is minus 1, 0 and 1, and hence we have 3 orbitals, right? And each of these 3 orbitals, they consist of 2 sections called as lobes. They are not spherical, they are sections of lobes that on either side of a plane that passes through the nucleus. So the origin, this is going to form the nucleus, and then we are having on the sides these 2 lobes, and the probability of finding the electron is going to be equal in both the lobes. Okay, and that is going to be 0, the probability density psi square, this is 0 on the nodal plane. Okay, and now these are all directed according to the various coordinates. The px directed towards the x coordinate, we have py directed towards the y coordinate, and the pz directed to the z coordinates. So they are all directional in nature, you can see from the diagram, and the shape is also called as dumbbell shape because of the resemblance to the dumbbell that is used by boys in the gyms to exercise. Okay, and the size, the shape and the energy of the 3 orbitals, they are identical. And when the orbitals, they have same energy, they are called as degenerate orbitals. So remember this term, what are degenerate orbitals? These are the orbitals which have same energy. Okay, and the lobes, you can see they are considered, they are lying along the XYZ axis. So for the 2p, we have the designation as 2px, 2py and 2pz. Fine. And the greater the value of n, just like the s orbitals, larger is going to be the size of the p orbitals as well. 4p will be greater than 3p, will be greater than 2p. And what about the nodes for the p orbitals? We have a general formula for p orbitals as well. N p orbitals will have n minus 2 nodes. N s orbitals had n minus 1 nodes, n p orbitals have n minus 2 nodes. So this means 4p has 2 nodes. What about 3p? Well, 3p will have 1 node and 2p will have 0 node. Next we have the d orbitals, and for d orbitals L is 2. So the minimum value of the principal quantum number n, this has to be 3. So the d orbitals, they start from 3d, then 4d, 5d, and so on. And they are going to be 5m values for L2, and they are going to range from -2 going up to +2. And therefore, we have 5 d orbitals, which are dxy, dyz, dxz, dx square y square, and dz square. And all these 5 d orbitals, they are equivalent in energy. Hence, they are also called as degenerate orbitals, as we studied even while we were studying the p orbitals, that they px, py, and pz, they are also degenerate orbitals because they are equivalent in energy. Now we have the diagram, the boundary surface diagrams for the 3d orbitals. So you can see over here the coordinates and the naming of these d orbitals. Well, there are going to be 4 lobes for each of these orbitals, as you can see, and hence they are called as double dumbbell also. One dumbbell was p and 2 is d, right? And how do you draw these? Well, let me explain you one of them. These 3 dxy, dxz, and dyz, they are all similar in shape. Like if we have dxy, what you do is you take the two coordinates x and y, and in between x and y draw the 4 lobes. Okay, so this way. Remember that these lobes, they are not coming on the z axis. Okay, you are seeing this as a 2D picture, but actually it is 3D, and these lobes, they do not come on the z axis. Similar is going to be x and dxz. So here you just see the x coordinate and the z coordinate, and between the x and the z coordinate draw the 4 lobes. And similar, this is going to be dxz, yz. And then we have the 4th orbital, that is dx square y square. Here the probability of finding the electron is more on the x and the y coordinates. So the 4 lobes, they are, you can see, on the x and the y coordinates only. Fine. Next we have the dz square, which is different from all of them. Here we have 2 lobes which are on the z coordinate, and then these 2 lobes which have fused to form a ring around these 2 lobes of the z coordinate as a ring. Okay, so this is called as the dz orbital, dz square orbital, and this orbital, this is also called as a baby soother shaped orbital, right? So baby soother is the one which is put into the mouth of the small children so that they stop crying. So this is quite similar to that, and it is also sometimes called as a donut shape. So right, I hope all the 5 3D orbitals, they are clear to you, the shapes. So the shapes, therefore, of the first 4 orbitals, you have seen they are similar to each other and they are double dumbbell shape, while the 5th one, that is different from the others, and this has a baby soother shape. And now what about the nodes? Well, first of all, the radial nodes. Do you know what are radial nodes? The nodes that we have been seeing while we were drawing the graphs for the psi and I, r, and psi square and r. Okay, so there we were seeing the wave functions as a function of radius, and there we saw a node in case of 2s, right? You saw that. So that is a radial node because that is a function of the distance, or if you can say that at a certain distance from the nucleus, the probability of finding the electron is 0, and that node that is formed, that is called as a radial node. Right, so we discussed that for ns orbitals, the radial nodes, they are going to be n-1. For the p orbitals, they are going to be n-2. So these are the radial nodes that we were talking about, and they are dependent upon the distance of the electron probability from the nucleus. Okay, so where there is 0 probability, that was a radial node because that was a function of the radius. Okay, so these radial nodes, they are spherical regions where the probability of finding an electron is 0, right? So this is meaning that this is at a fixed distance from the nucleus. But then there are angular nodes also. So what are angular nodes? Well, the angular nodes, they are going to be at a fixed angle from the nucleus. The radial nodes, they are spherical, and angular nodes, they are flat planes. Okay, so the probability density functions for the np and the nd orbitals, they are zero at a plane passing through the nucleus, that is the origin. Okay, so a plane passing through the nucleus, that plane, there is probability of finding the electron to be zero, and that we call as a angular node. So to understand this, take the example of the pz orbital. For the pz orbital, the direction of these orbitals in the z axis. So we have a nodal plane passing through the nucleus, or the origin, you can say. The plane is going to be the xy plane. How can you understand? Well, if you take a pencil, point it towards the z axis, or you say the x-axis. Okay, you are taking a pencil horizontally, and take a paper and pass the paper through the pencil. In the center of the pencil, place it. What are the coordinates of that paper going to be? It is going to be in a YZ plane, right? So for the px orbital, it is going to be the yz plane. For the pz orbital, it is going to be the xy plane, and so on. So this is a nodal plane, this angular node, where the probability of finding the electron is going to be again zero. In case of the dxy orbital, there are going to be two nodal planes passing through the origin and bisecting the xy plane containing the z axis. So these are the angular nodes. And what are going to be the number of angular nodes? They are going to be given by L. For D, that means there are going to be two angular nodes. For L, there is going to be one angular node. For S, there is going to be zero angular node, right? So the number of radial nodes, this is given by the formula n minus L minus 1. So you have seen for S, 1s, there was no node being formed, right? So here, if you put the formula for 1s, you have n to be 1, s is going to be 0, and this is again 1. So 1 minus 1 is 0. So we have 0 radial node for 1s. Similarly, we will be having 0 angular node for 1s, and the total number of nodes, again, both adding both of them, that is given by the formula n minus 1. So that is going to be again 0 in case of 1s, right? So you can put the formulas and calculate the nodes for the various orbitals, and this is one of the questions which is frequently asked in the examinations also. So now the total number of nodes, this is given by n minus 1, that is the sum of the L angular nodes and n minus L minus 1 radial nodes. So I hope this is clear to all of you. So that would be all for this lecture. I hope all the shapes of the different orbitals, the s, p and d, they are clear to you. And as I told you, the f orbital shapes quite complicated. They are not a part of our curriculum, so we would not be seeing those shapes for the 7 f orbitals, right? So next lecture, we would be starting on to the discussion that is going to lead on to the electronic configuration of the various elements. I hope you will join me for the next lecture on this very interesting topic. If you have any difficulty in this topic that we discussed today, or any other topic related to chemistry or this course, please do feel free to mail us at h2ochemistry@gmail.com. You can also put your any difficulty in the comments section also. We would be really glad to help you. And if you've liked the lecture, please do click on the like link. That motivates us to work more for you. And then do subscribe to the channel H2O, and then also click on the bell icon to get a notification as and when we put up a new lecture for you, a new course for you. So bye, have a nice day, enjoy yourself.